Oh, that's right. Yeah, that's right.
Would you say if someone was walking there?
So it says, is this the recording?
Yes.
You were right.
Okay. I guess we can get started.
Should we wait for that?
Yeah, but,
We can give it another one.
okay, sure. I can turn off my video in the room. All right, good. But I can start introduce Madeleine today. So she's from Uppsala, doing a postdoc there. She's also a Marie Curie fellow over the pandemic periods.
Yeah, the worst.
Yes. So, but right now you have another project with a Swedish geological survey. It's working on lithium and catchment. But her topic during the Marie Curie fellow is about nickel isotope. So, and then she did her PhD in Cambridge. That's why this is there. And then lithium isotope was a topic for your PhD.
Yeah.
So that's your old favorite.
Yes.
Yes, still the favorite. Yeah. So today, she will take us to India, and then looking at the lithium isotope from this gigantic river from the mountain range, and then see what that can tell us about the silicate weathering, which is why we have the CO2 so low here. Otherwise, we'll be like Mars. Yeah. Okay, the floor is yours.
Okay, thank you. It's really nice to be here. Thanks for coming. So now we're going to spend maybe the next 40 minutes talking about lithium isotopes in Himalayan rivers and what we can do with lithium isotopes and what it can tell us about silicate weathering. So I started a lot of this work during my PhD. So I want to acknowledge the work of and the input from my supervisor, Mike Bickle. So what you're looking at here is essentially the birth of the Ganges. So this is up in the northern parts of India, just at the base of the Himalayas. And here we have the confluence of the Alaknanda River and the Bhagirathi River. And just where they meet, the Ganges is forming. And then it's flowing down on the Ganges floodplain. And Ganges is, of course, one of the most important rivers on our planet. Compared to its drainage area, it actually provides a disproportionate amount of solutes and especially sediments. And most of these are generated up in the Himalayan mountains. So although we've done some work on the Ganges floodplain as well, today we're going to focus on the Himalayan mountains and what's happening there. So I'm not really sure about what kind of background you're coming from here. So I'm going to ease you into the topic. I'm going to give you a background about weathering, about lithium isotopes, and then we're going to look at some nice field photos. Then we're going to look at how lithium isotopes vary across the Himalayan mountains. And then we're going to talk about a reactive transport model, which is really the new thing that we contributed with this study. But silicate weathering, why are we so interested in silicate weathering? Well, the short answer is that it's a long-term carbon sink. So silicate weathering provides this negative feedback with our climate, and it draws down CO2. So you're probably familiar with the long-term carbon cycle and the fact that it's very closely linked to our silicate cycle, or our rock cycle. So CO2 is always emitted to the atmosphere from volcanism, so both on land and in the ocean at mid-ocean ridges. And we also have decarbonation reactions at depth, so metamorphism at subduction zones, for example. So this emission of CO2 is completely governed by the internal heat engine of the planet, right? But once in the atmosphere, the CO2 will react with water and it creates carbonic acid. And carbonic acid is a very weak acid, but if you give it enough time, it will dissolve the rock on the continent. So carbonic acid will dissolve both carbonate rocks and silicate rocks. So these are very generalized reactions, but essentially if you have 1 mole of calcium carbonate, you need 1 mole of CO2 to dissolve it. If you have a silicate rock, on the other hand, you need about 2 moles of CO2 to dissolve it. So this becomes important later on. But carbonic acid will dissolve the rock, we're creating all of these solutes, so lots of cations, and we have our bicarbonates here. And all of these solutes, they're transported by rivers, and rivers kind of create these huge conveyor belts that connect the continents to the ocean. And this is why we study rivers, because it really gives us an integrated view about everything that's happening on the continent. Once in the ocean, this bicarbonate will recombine with calcium to form calcium carbonate. This will be buried on the seafloor, and we kind of start this cycle all over again. But here we see that when we're precipitating calcium carbonate, we're actually releasing 1 mole of CO2 again. So now this is why it's important what type of rock that we're weathering on the continent. So, you know, carbonate weathering, we're using 1 CO2, we're releasing 1 again. So carbonate weathering is actually a long-term carbon neutral process. We don't really care about carbonate weathering. But silicate weathering, on the other hand, actually draws down CO2. So this is what we want to look at. This is our negative feedback mechanism with climate. Noisy weathering is a quite slow process, right? On a yearly basis, we don't actually draw down that much CO2. But it's when we're looking at really long time scales, that even if we have a small shift in this flux, we can see a big impact on our climate. So you probably recognize this plot. This is oxygen isotopes in benthic forams during the Cenozoic. And we have this kind of global cooling trend. So benthic forams, this tells us the temperature of our bottom water on our planet. And we've gone from something like 10, 15 degrees to what we have today, you know, 2 or 4 degrees or something. So we've had this general cooling on our planet. And there are many theories and many things working together to why we have this cooling. And it's been very hotly debated. We can leave it at that. But one of the kind of prevailing theories is that we have the uplift of the Himalayas sometime 50 million years ago, and that created some kind of hotspot for silicate weathering and CO2 drawdown. So essentially this massive orogeny just created so much fresh material. And also we have the orographic monsoon system, right? So we've just kind of created this hotspot for weathering and CO2 drawdown. Like I said, it's been very debated whether or not this is true and how silicate weathering actually relates to the CO2 drawdown. But there is some quite compelling evidence to suggest that we do have an increase in the continental flux during this time. So in this top graph here, we have the radiogenic strontium composition of seawater. And we see that sometime around 40 million years ago, we have this huge increase in radiogenic signal. And this has been interpreted to be because we have an increase in silicate weathering. So silicate minerals on the continent are very old, right? So average crust is something like 2 billion years or so. So we've had lots of time to accumulate this very radiogenic strontium. So we have lots of 87 strontium in the continental crust. Hydrothermal input in the ocean has a basaltic composition. It's very young rock. We don't have a lot of, we have a very unradiogenic composition. Carbonate rocks also have a very unradiogenic composition. So this increase here was suggested for a long time, like, okay, increase silicate weathering, story's done. But it's always more complicated than that, isn't it? So it's been shown actually that carbonate rocks in the Himalayas have an incredibly radiogenic composition. That's because we have metamorphism. So we have lots of metamorphic exchange between silicate and carbonate rocks in the Himalayas. So we don't actually know how much of this increase is due to silicate weathering or how much of this is actually just carbonate weathering. And remember, we don't care about carbonates. It just kind of obscures this picture. So that has really complicated things. But we're lucky because there are lots of other isotopes we can look at. And in this graph here, we have lithium isotopes. So you see during this time, we also have an increase in the lithium isotopic composition of seawater. And this is interesting because lithium is almost entirely hosted in silicate minerals. So we can kind of ignore everything that's happening with carbonates here. It doesn't matter to us. So that's not what we're picking up here. So the global ocean has gone from something like 22 per mil in the early Paleocene to 31 per mil that we have today. So a 9 per mil rise. So this was also interpreted then, okay, increase in silicate weathering, and I'll get into the details about how that works later. But since this record was published, obviously there's been, again, lots of debates to why this is. Why do we have this? Is it because of the Himalayas? Is it a change in our weathering setting and erosion? Does it have to do with something like fluid residence time in the mountain? Is this all due to a change in climate, or is it a shift in the marine sinks? I mean, mind you, these are very different interpretations. And it seems like the common way around of doing things, that someone will first publish a curve, and then the rest of us has to spend decades trying to figure out what this actually means. So I guess my point here is that, I guess as a whole, the goal of our field is to understand this curve better, and to understand how does this relate to our climate, how important is silicate weathering, all of these things. But it's proven quite difficult to show what actually controls lithium isotopes today in rivers, for example. So that's what we're trying to do now. What controls lithium isotopes? What can we say about weathering using lithium isotopes? Okay, so that's the basics with that. So let's just look at lithium isotopes then. So like I said, lithium is quite interesting because it's almost entirely hosted in silicate minerals. We can kind of completely circumvent this whole carbonate versus silicate story then. Another thing that's interesting is that we don't really have any biological uptake of lithium. That makes the story a lot easier. So obviously, if you want to look at silicate weathering, it could be very useful to look at silicon isotopes, but silicon is really cycled through biology, so it becomes a little bit more hard to interpret that data. But we don't really have that problem with lithium, so that's a huge benefit. But the most interesting thing is that we have a huge fractionation of the isotopes during weathering processes. So as we're weathering, lithium 6 and 7 will kind of partition into different phases. So it means that we can use it to look at different processes and not just using it as a source tracer, but we can look at weathering processes. And you can see that very clearly in this plot here to your right. So here we have lithium isotopes on our y-axis, and we denote this by delta 7 lithium. And here we're looking at different rivers from around the world. And here in gray is the composition of the upper continental crust. And in open symbols, we have suspended sediments in different rivers from around the world. And in the filled symbols, we have the river waters, which drain these sediments. And we see that in every single case, the river waters are isotopically heavier than the sediments that they drain. And why is that? Well, the reason is that when we're dissolving a silicate mineral, and especially an aluminium silicate mineral, we'll do that incongruently. It means that we'll always form a secondary clay mineral. And this is because aluminium is essentially insoluble. You know, at the Earth's surface condition, we can't keep aluminium in solution. So the second we dissolve it, it will immediately reprecipitate as a clay. And when that happens, lithium 6 will partition into the clay, but lithium 7 will stay in the water. So essentially, the more clays we're forming, the heavier our waters will become. We can see that very clearly in this graph here. Here we have a river waters in blue. We see the isotopically heaviest pool. The kind of average composition of large rivers is around 23 per mil. And then sea waters actually are heaviest at about 31 per mil. And we see in brown here, we have the composition of rocks. So we see this kind of bimodal distribution. We have the upper continental crust at around 0, and then we have basalts, which are a little bit heavier at about 5 per mil. And then in yellow here, we have suspended sediments in rivers, and they're the lightest kind of reservoir of lithium here. And that's because they contain all the clays that we've been forming. You know, clays are very hydrodynamic. They'll flow up at the surface of rivers with the suspended sediments. So that's how the kind of lithium systematic works. Quite straightforward. The more clays we're forming, the heavier your rivers will be. So let's look at the field area. So I had the great fortune of working on this river called the Alaknanda River. It's a big river flowing straight across the Himalayan range in northwestern India. This is a part of the Himalayas. It's called the Garhwal Himalayas. This is just a Google Earth view of how the catchment looks like. So we're originating up on the Tibetan plateau, and we're flowing all the way down to the Ganges floodplain down here. And across here, we have these kind of major fault structures of the Himalayas. So you might recognize these names. We have the main boundary thrust, main central thrust, and the South Tibetan detachment system. And these faults, they kind of separate the Himalayan range into 4 major lithotectonic units, which have very kind of different characteristics. So up on the Tibetan plateau, we have something called the Tibetan sedimentary series. In the high Himalayas, we have the high Himalayan crystalline series, and then we've got the lesser Himalayan and out to lesser Himalayan series as we move south in the catchments. And like I said, these units have very different characteristics when it comes to both geology and things like climate, for example. So The river originates up on the Tibetan plateau. You see on the pictures here, it's very dry. We're completely in the rain shadow here from the mountain. So it's almost like desert conditions, right? We only have about 400 millimeters of rain per year, almost no vegetation, it's cold. And these rocks here, they're essentially completely unmetamorphosed rock, old seafloor that's just been uplifted. And then the river makes its way down to the high Himalayas. And here we have this very characteristic snow-covered peaks, huge relief, high elevation. I think the highest mountain in this catchment is almost 8,000 meters. So obviously it's very cold up here as well. So a lot of these catchments here, they're glaciated. So we have a huge range of kind of the size of sediments in these catchments as well. You can see the color of these rivers are a little bit milky because we have so much very fine grained material from the glacial grinding there. But then we also have these huge boulders being transported because we have huge landslides, right? So there's a large mix of different sediments being transported here. And the rocks in these areas are very highly metamorphosed. Obviously we have huge erosion rates in the high Himalayas as well. So I think it's one of the fastest eroding areas on the planet. So in a year, we're uplifting everything by 3 millimeters per year at least. So it's a lot. Then we go more south and we get to the lesser Himalayas and the outer lesser Himalayas. And here it's a completely different climate again. Now you see it's very dense vegetation, it's more subtropical, it's incredibly hot and humid. And there's a huge variation in relief here as well. So when you're up in kind of the northern parts of the lesser Himalayas, we still have this very steep flanks, lots of landslides, and we're still up at about 2,000 or 3,000 meters altitude. But then towards the south, here in the outer lesser Himalayas, is more flat. Well, I wouldn't say flat, we're still in like the Himalayas, but we call it the foothills, so it's more hilly, not super mountain peaks. So that was kind of one of the reasons why we want to work here, because in quite a small area, you get these huge differences in all these physical parameters that we know should have an effect on chemical weathering. So we have things like relief, elevation, and erosion really increasing to the north in the catchment. And then we have more our kind of climate variables like temperature, rainfall, and vegetation is really increasing to the south in the catchment. So hopefully when we look at the data, we should see a very large spread in our river data that kind of reflects all of these differences. And hopefully, the end goal is to try to figure out how each of these parameters affect our lithium isotopes. So if you just look at the data straight away then, here we have lithium isotopes on the y-axis, and we've got our lithium concentrations in our river waters here. So all of these colors correspond to the different catchments that we have in here. And then in gray in the background is just data from a few other rivers from around the world. And we see at least straight away that, okay, it's cool. Our data seem to span the entire global range. So that's good. We can try to pinpoint lots of these kind of parameters here. What we also see is that this negative correlation between isotopes and concentration, right? So here in the high Himalayas, we seem to have very low isotopic compositions, but very high concentrations. And then as we go south in the catchment, we get higher isotopic compositions and lower concentrations. So here we have more and more clay formation the more south we go in the catchment. So as we're forming clays, we're kind of reducing our concentrations because the lithium goes into the clay. And at the same time, we're fractionating our isotopes. So our waters get pushed up in isotopic composition. So that's our kind of initial interpretation of this data. Okay, more and more clay formation, the more south we go. Obviously, you want to have a look at how your sediments vary, so how your bedrock is varying. So the bedrock will kind of provide the starting points for your waters. It's the bedrock that dissolves and creates the solution, solutes in the water, right? So here we have the isotopic composition and concentration of our bed loads in the catchment. So it's really useful to use a bed load sample, so like just kind of the sand at the bottom of the river as a proxy for your bedrock. So we know in these catchments that our bed loads are very minimally altered, so they're very good, they kind of reflect the bedrock composition. And it means you can just take a few samples of the bed load because it provides kind of an integrated composition of the whole catchment of all the rocks that are eroding there. It will be quite difficult to go and try to sample, all the different types of rock in the high Himalayas. But here we see we do have a few kind of flyers in our data set here. So in gray, again, is the upper continental crust composition, but we see that especially in the high Himalayas, we have some sample which have very, very high concentrations of lithium, and this is on a log scale. So we have some samples here that have 500 ppm lithium. And that's because, especially here around the South Tibetan detachment system, there's lots of leucogranites that are outcropping there. And leucogranites very often have pegmatite veins. And pegmatites, they contain lots of lithium-rich minerals, so like spodumene or petalite, something like that. So that's contributing lots of lithium with a low isotopic composition, but with a very, very high concentration. And then we have a couple of samples here which have a very high isotopic composition, and that's from this green catchment here. And we think that's because there's some basalts in that area. So basalts in general have a slightly higher composition, around 5 mil. But then if they've been altered on the sea floor, they'll tend to have a much higher composition because they're reacting with seawater, which is very heavy. So this is obviously before they were uplifted, and now they're eroding. So that's what we're seeing here. But of course, we need to correct for this composition, because this is what kind of creates the composition of our waters, right? So we need to correct for how the lithology looks like. And we do that very simply by just subtracting our solid or our sediment composition to our fluid and just dividing our concentrations with each other. Then we've kind of taken care of this difference in lithology. And if we do that, we see that, okay, still has a kind of negative trend here. I guess our initial interpretation still holds true. We have less clays forming here in the high Himalayas, more clays forming in the lesser Himalayas. But now we see that our data has kind of grouped into 3 main groups, and each group seems to have a positive correlation between lithium isotopes and concentration. So obviously this is something we need to try to understand a little bit better. So we need to find or come up with a good model to describe this. So that's what we did. We have developed a reactive transport model to try to understand this a bit better. Before I talk about the details of what we've done, I want to show you how you normally would model this kind of river data. So it's very common that you use a batch fractionation model or a Rayleigh fractionation model. And these definitely have their strengths because they're very simple. It's very, very easy to fit your data with a model like this. And it's quite easy to understand what they do. So here we essentially just say we have our isotopic composition of our water. We have some initial composition here. Then we're just removing a factor F of lithium as we're forming clay. And as we're removing lithium, we fractionate the isotopes. That's all there is. We're just removing as we're forming clays. This fractionation factor has a value of about 17 per mil. So we'll just remember that. So these are, useful, simple, easy to use. When you use a batch model, your river water can only ever evolve to the value of your fractionation factor, essentially. So you can only model waters that have an isotopic composition that's a maximum 17 per mil here. If you have rivers that have a higher composition, we have lots of rivers with higher compositions, you need to use this Rayleigh fractionation model. And then now all of a sudden, the value of your isotopes of the river can increase to much higher values than your fractionation factor. And this is an example from Mathieu Dellinger's now seminal paper, I'd say, where he's been looking at isotopes on the Amazon floodplain. And here we see that mountainous rivers, so the rivers that drain the Andes, they all fall on this kind of batch fractionation line. And everything on the floodplain, we have much higher compositions. And here we need to use a Rayleigh fractionation model to fit this. So yeah, sure, this fits the data very well. But actually, this doesn't really give you a mechanistic understanding of why lithium is being removed or why your compositions look like this. And another thing is that here we're only looking at, removing lithium from clay formation. We're completely ignoring one of the most important part of weathering, which is the fact that we actually dissolve rock to provide lithium here. So we need to think about that. What happens if we start dissolving rock here? So that's what we've been trying to do. So we've been trying to add a little bit of nuance to this maybe. Is there more we can get from this than simply just a value of F, how much we're removing? There must be more we can get. So we developed a reactive transport model, and I'll just paint you a little picture of how this works. So essentially we have a rock, which has a lithium concentration and a lithium isotopic composition. And then we have water flowing through these rocks. So this can be rainwater that infiltrates down to the rock. And this water will flow along flow paths in the rock. So these flow paths will have different lengths, they will have different depths, and they'll have different water fluxes along these flow paths. And all the time we're dissolving rock, so we're adding lithium to the water, and a fraction of this lithium is going to be removed through clay formation. And all of these factors then combine, and we get our lithium concentration and isotopic composition of our rivers. And that's what we can measure. So essentially we measure this, and we're trying to figure all of this out. Can we do that? So this is just in equation form, what I just showed you. We have our kind of concentration equation here and our isotopic equation here. And we're saying that the variation with time just equals our advective flux of lithium, so how much we're transporting through the system, plus how much we're adding from rock dissolution, minus what we're removing from clay formation. So it's a lot simpler than it looks. And here we're kind of baking in this fractionation factor here. And what we do with this type of equation is that you normalize it, or you non-dimensionalize it, so that all catchment will be comparable with each other. And then we integrate it. And then we end up with analytical solution that looks something like this. So here we have an equation for our concentration. So this is our rock normalized concentration. So exactly the same thing we did in the first plot when we were looking at the data, and our isotopic equation here. And what we find is that both concentration and isotopes really only depend on two dimensionless variables. We call this the Dom-Curler number and the net partition coefficient of lithium, or K-net. So essentially what you do here is a bit of magic. You just take all of the unknowns that you don't know, and you lump them in together in as few possible variables as you can. And then you can solve your equations for these two numbers, and then essentially try to work your way backwards and try to figure out what this means in terms of fluid fluxes and clay formation and that kind of thing. But I'll show you, just show you what these kind of mean a little bit more. So if we start with our net partition coefficient, or K-net, here we have this F factor, again, what we just talked about in the other models as well. So this is our fraction of dissolved rock that forms clay. And we just multiply that with our partition coefficient of lithium between the clay and water. So essentially with the K-net variable, we ask ourselves, how much clay are we forming and how much lithium is going into these clays? If you have a higher value of K-net, it means you have more lithium in clays. Simple. The Dom-Curler number tells you the relationship between your silicate dissolution rate to the kind of fluid flow path length and the fluid flux along this flow path. So this together gives you your fluid residence time. So essentially, you ask yourself, how important is chemical reaction compared to the advective transport in the system? Essentially, if you have a high Dom-Curler number, it means you have a higher dissolution rate, or a longer residence time. Sorry. If you have a longer residence time, it just means you have a longer time to react, right? So yeah, just to give you an example. So yeah, one thing, we have a lithium concentration, we have our isotopes, we can now calculate our K-net and ND, and it's quite neat. So each of these equations, they provide an analytical solution with essentially one answer. So we can only have one combination of K-net and ND to give us the lithium compositions that we have. So that's quite good. Gives us a good framework to interpret our rivers with. So I guess I just want to show you here, one of the easiest thing to constrain in this K-net variable is actually this F factor. So how much clay we're forming, essentially. So the F factor here just tells you how much clay you're forming. And we can consider, we can calculate this by looking at just the stoichiometry of weathering reactions, and remembering that aluminium is essentially insoluble, right? So for example, if we've got an albite and we dissolve this, we know that we have to form 0.33 moles of kaolinite, because the aluminium has to go into the clay mineral. Or in terms of volume, if we got 1 cubic centimeter of albite, we're going to have to form 0.41 cubic centimeter of kaolinite. So we can calculate this quite easily, this F value. And I guess the interesting thing thing to look at here is that as we're kind of moving down this table, we're moving into more kind of difficult to dissolve minerals. So it's quite easy to weather an albite, but it's really hard to weather a muscovite or a mica, you know. So here we're essentially increasing our weathering progression or weathering intensity downwards in this table here. And as we do that, the value of this F, and hence the value of our K-net, will increase as well. So essentially, the more, you know, higher weathering intensity or more weathering progression, the higher the value of our K-net is going to be, very systematically. So we can just remember that when we look at this. And this is what I call the reactive transport grid. Here I've just solved both of these equations at the same time, and then contoured it with different values of these K-net or ND variables. So here you have in these dashed lines, I don't know if you can see it, but yeah, in these dashed lines here, we have different values of this ND variable, Don color number, and in the solid lines, we have the values, different values of K-net. So ND is increasing this way, K-net increasing this way, and the same in this grid here, we see how they increase. And we end up with two different grids here because we kind of have two different types of scenarios. In this first grid here, we're looking at very early stages of weathering. So for example, the albite dissolution. And here, we're providing more lithium from dissolution than we're removing from clay formation. Remember, the F factor we were looking at is less than 1. So here, we're going to actually build up our lithium concentrations, the more and more we dissolve, because we're never removing as much as we're dissolving. But then as we start to shift our weathering reaction, we can actually start to remove more lithium than we're dissolving. And that's obviously only possible because we have advective transport of lithium as well. So essentially we've accumulated so much lithium in this first scenario that now here we can shift our weathering reaction and we start to precipitate more than we're adding from dissolution. And essentially how the river waters will evolve is that, you know, let's say water is percolating through the rock, and as the rock starts dissolving, we'll quickly start to increase our lithium concentrations because we're dissolving the rock, right? And then we'll essentially follow these trajectories of K-net. So that you can see this K-net as kind of mineral reaction lines. So they all represent different, or maybe mixtures of different mineral reactions. So the water will evolve along these mineral reaction lines towards higher values of this Don color number, because we're increasing, you know, dissolution more and more and more. So it will kind of follow these lines like this. And then it will stop up here at 17 per mil, which is the value of a fractionation factor. And it will happily stay there until something changes, until we get more intense weathering, or more progressed weathering. So now all of a sudden we're going to change the F value, we're going to increase our K-net enough that we end up in this grid up here. So now we're starting at 17 per mil, which we left up there. And as again, we're following these lines of K-net towards higher values of ND. And now our samples are doing a bit of a funny loop here. And that's because now, obviously, we're precipitating more, removing more than we're adding. So our lithium concentrations are quickly going to decrease again as we're removing more and more. Our isotopes are going to increase more and more. So here we're up, you know, in this kind of theoretical grid, we're up at about 50 per mil already. So we can push up the isotopes a lot, but eventually we're going to decrease the lithium concentration so much that anything that we're adding from dissolution, you know, that has a very low isotopic composition, we're quickly going to decrease our isotopes again. So that's why it's doing this kind of loop back. And again, it will kind of happily stay at 17 per mil when it's in perfect steady state. So that's how it looks like. And when you put these grids together, it looks like something like this. And now when we add our samples to this grid, this is the happiest I've ever been in my life. It's very rare that data somehow fits a model like this. So now we have these 3 groups of data, right? And it seems like they very nicely follow these lines of K-net. So these kind of mineral reaction lines towards higher values of ND. So there are a few observations we can make straight away. The first observation is that they lie on both of these grids. It means we somewhere in the catchment here, we have a shift in weathering processes or a shift in the type of weathering we have. So all of a sudden it gets more intense weathering, more progressed weathering. And we can probably see, so here, the second observation is that we have very like I said, very kind of tight values of Knet, but a larger range in ND. And we can see that clearly in this type of graph here when we just look at Knet versus ND. These are our three groups. And yeah, quite similar values of Knet within each of these groups. So obviously it's very tempting to put some kind of mineral reaction label to this. This is just made up because you need to obviously have better constraints on your actual catchments. What type of mineral are you weathering? What are you forming? But it's clear to see anyway that we have our kind of group with the lowest values of Knet. Have this, this reflects the earliest stages of weathering where we don't have much clay formation at all. Then we have our intermediate group, where we have a little bit more intermediate weathering reaction. And then eventually, as we get down to the lesser Himalayas here and outer lesser Himalayas, we have much higher Knet values. So we must have a reaction here that consumes more lithium than what we're adding from dissolution. And the last observation here is just that we do have this grouping of the samples here, depending on where we are in the Himalayan mountain belt. So this kind of group with the most progressed weathering we have down here in the outer lesser Himalayas and lesser Himalayas. I mean, this kind of makes sense. It's hot, it's humid, we're really promoting weathering reactions here. And also importantly, our erosion rates are much lower here. So rocks spend about 3 or 4 times longer in the kind of weathering reactor in the lesser Himalayas compared to in the higher Himalayas, where rocks are, just eroded and taken away and don't have time to weather. And that's why we have this higher Himalayan groups at these more less progressed weathering. Sorry. And interestingly here, we still have some of the lesser Himalayan catchments in this intermediate group. And these are all the kind of bigger catchments, the mouth of these bigger tributary rivers. So all of these rivers actually drain into these samples, but you don't pick up that signal at all when you're looking at this main stem sample. And these big rivers, I mean, they originate really up on the high Himalayas from the base of glaciers. And there you have really early stage weathering. And obviously they have a very high lithium flux because you don't have a lot of clays forming there. So the lithium is actually dissolved. So that's going to be your dominant flux that you're looking at. And that's what you're picking up in these samples. And that's the same in this kind of earliest stage weathering group. Here we have our main sample. So the outlet of this entire river basin only reflects the weathering that's occurring up on the Tibetan plateau. So here we have the absolute earliest stage weathering. We have very high lithium flux because we don't have any clays that are taking up this lithium. And this is all that we see at the base of this catchment. So I guess the point here is that if you want to sample rivers and you take one sample from the base of the catchment, you're going to look at this and you're going to think, there's no weathering going on in this catchment. There's no CO2 drawdown. But actually you're missing everything because all the lithium that's being taken up in clays is just kind of stuck in the soils here, right? So you're not seeing that flux of lithium. But yeah, that was a bit of a side note, but that's kind of something to think about when you're planning field expeditions and stuff like that. But yeah, so in conclusion, what we did in this work was that we developed this reactive transport model, and that looks at the dissolution of rock and how lithium is added to the water. We're looking at the removal of lithium from clay precipitation and also how advective transport and kind of this hydrological component will affect lithium isotopes. And we find that the lithium composition is controlled by 2 dimensionless variables, so our Knet and our Dom-Köhler numbers. And the values of this Knet is really useful because it provides us a really kind of direct assessment of what type of mineral reaction that is occurring. And that's very useful when you compare weathering in different catchments. And the Dom-Köhler number, it gives us information about how much silicate weathering we actually have, or dissolution that we have. And it tells us something about fluid residence times as well. And using this model then, we can see that we have this clear transition in weathering across the Himalayan mountain belt. And it seems like we have at least 3 dominant weathering reactions going on here. And then also we just see that the main river, the flux at the bottom, only reflects what's happening on the Tibetan plateau. Okay, thank you. I'll happily take any questions. Everyone's awake, I don't know. Oh, that was a lot faster than I thought it would be. Oh. Okay, good. When I practiced, it took like 50 minutes. Oh, God. Do you have any questions?
challenge the speaker.
Yeah, I'm still trying to sort of get myself around to what extent sort of, resuspension or this murky rivers, this balance between, resuspension and weathering, and how that is essentially reflected in this ND or Thermocular.
Yeah.
And then to what extent that is some sort of a reflection of flow speed of because in principle everything's flowing all the time in these rivers. So
so
the
that's
retention time is different.
but then retention time then becomes a scaling question, right? To what extent we're looking at particular sections on your river that may have a certain.
So one
flow
important
speed.
thing is that we kind of consider this as happening in the rock. So in the sediments in the river, we say that they don't really weather. So it's the groundwater in the rock actually. So it's the residence time of those. So these sediments, so the water at least travels really, really fast. It only takes about 2 or 3 days for the water to travel in the river down to the Ganges floodplain. And we did some mass balance calculations to show that we don't have really any weathering of the sediments within the river channel itself. Because everything's just flowing so fast, essentially, until it gets to the Ganges floodplain. Then this kind of slows down. You have way more weathering of the kind of like sediments on the banks and the, what's it called? I forgot the name, but the sediments on the banks, essentially. You have way more weathering then. But up in the mountains there, we kind of envisage it as being just through kind of pores and cracks through the rock, essentially, mostly actually from cracks in the rocks. So I don't think the resuspension of the sediment should make such a big difference in that setting, if I understand you correctly.
Yeah, I really have to get myself around. I maybe asked really long questions.
No.
Not thinking about big picture. So when you're down on the plane, you say your lithium isotopes reflect pretty much the rock.
Yeah. So it's very low isotope composition.
You just don't see basically the precipitation reactions.
Yes.
That are going on in the riverbed.
Yeah. That's only, that all of these catchments in the lesser Himalayas, they have, there's lots of clay formation there. So, the isotopes are very high in these rivers, but the concentration is so low in these rivers that that signal is kind of just swallowed up by the high flux from the high mountains. That's another interesting thing, actually, if you remember the Cenozoic curve that's increasing, right? And a lot of theories say that, it's because we have the buildup of the mountains. So we have lots of weathering, long residence time, waters, and, it must be the mountains that do it. But from what we see in all the data is the mountains themselves have really, really low isotopic composition. So it's not the mountain weathering that's drawing up this lithium and seawater, but it's probably the development of a floodplain. So you have the synorogenic, creation of the Ganges floodplain, and that's really when all the isotopes start going up. So that's when you get all the weathering, but it's not the mountains themselves. Well, it's indirectly.
So if you were to take a pore water pool in the floodplain,
good question. It's interesting. They've taken lots of cores and looked at the groundwater. I can't remember if they've looked at they must have, right? They were looking at the groundwater, and first you see that the isotopes increase a lot in the groundwater. So it increased and then it goes down a lot. So deep in the Ganges floodplain, the groundwaters have an isotope composition of about 6 per mil. So there, they say that it's because you have dissolution of clays down there. So the clays have the lightest composition. And down there, weathering is apparently so intense that you dissolve clays as well. And then you get a light isotopic composition.
dissolution of clay.
Yeah, that's like
What
But
is
do you-
the thermal gradient?
yeah, could be. I mean, there's
But do you have
lots of hot springs up in the Himalayas, right? You have very light composition, so it could be that it's a thermal gradient.
So what about concentration profile?
Concentration. Oh, you're asking difficult questions. I can't remember. Yeah, I'm trying to remember. This was like years ago I read this paper. I would guess that it increases a lot. So if you have, I mean, if you have such light composition, you tend to have very high concentrations because you probably either dissolve clays or you haven't formed clays in the first place. So like I said, if it's a thermal gradient, you're probably not forming so many clays either. Like the hot springs, I mean, the Himalayas is just kind of peppered with hot springs as well. And they have incredibly high lithium concentrations and really low isotopic compositions. So they might have a composition around 2, really reflecting just the rock composition. So I think that's probably what you see in the Ganges Delta. But that's the depth. I can't remember how it looks like all the way down to the depth.
So there's, if I understand this correctly, this page you have these, how should I, what did you call this? These different regimes.
Yeah, that's it.
Right? So the rock types, how different are they in these different regimes?
They're quite different. They're
And-
very different.
But that
Mm.
you don't really see that in the nice.
So you can. It was in the beginning of the beginning of history of lithium isotopes. People were saying that lithology doesn't matter at all because this clay formation kind of overprints anything you see with lithology. But I mean, it's quite clear we do have a big difference. And if you remember, I showed how the bed loads look like, and there is quite a big spread.
Right.
So you have to normalize your water data or account for that somehow. So we just normalized it too and hope that that's the best way of doing it. But that seems to be how most other people do it as well. Just normalize it to that. But I mean, you have to.
Okay, so you do this normalization, but still you say when they're out in the floodplain, then that's really when the alteration is taking place. So there it's basically all landing in this one big.
Let me show you.
So because the particles ultimately landed, right? So that's
Yeah, so I say we obviously still have a lot of alteration in the mountains, but the flux isn't high enough to impact the ocean or whatever you'd say. Wait, I have a graph. I thought. Here. Here. So this is actually how lithium isotopes evolve on the floodplain. So this is the kind of base of this catchment that I was just talking about. So this is the Alaknanda here. We have a very low composition because it's just, Tibetan plateau composition. In reality, our samples span from here up to here, right? So this should be a vertical line here, really.
so I don't see anything.
We don't see it, right?
1 second. Now you can see it. Okay. Okay, let's do that again. So here, this is distance downstream from essentially this last sample point I was talking about. So the outlet of the catchments I was talking about now, that's here. And then as we move south along the floodplain, these are all the rivers here. They very quickly increase in isotopic composition because here we just weather, and then they reach a steady state of about 22 per mil. So here, essentially, all rivers get up to this value. I mean, the rivers I was just talking about, now I'm just showing the outlet here, which only reflects the Tibetan plateau, right? But really, my sample should really lie like a vertical line all the way up to 32 per mil here. So we do see, lots of weathering as well in the mountains. You just don't see it in this one sample point. If this is the only thing you want to, sample, this is common. Papers do this all the time. You take one sample from each big river, but it doesn't really tell you what's actually going on there. You're missing a big part of the story because you would look at this and think, but there isn't any weathering there. When in reality, you should have a line that looks like, going like that.
Okay.
Yeah.
But then, okay.
Just a question, I'm not in the field, so I'm
It's okay.
a geologist,
Yeah.
not geologist.
Mhm.
I mean, in your work, you assume that all the rocks that form what you call the upper crust has, in a sense, the same behavior to weathering. So they are weathered. If we compare, for example, the granite and light, we know that we will weather more light and granite. So,
Yeah.
In this study, you cannot take into account the difference that you have, for example,
guess-
in the Himalayan.
I guess we do in a way with the value of k-nets that we get out. So it's not something we need to consider before we model the data. But once we get the kind of model output out and we get this value of k-nets, we could kind of see, do we have something that's easy to dissolve or something that's hard to dissolve? That's about as far as we can take it with just this model. You can compare it, and then but it's hard to see it in any more detail than that. You would have to do you can obviously do a more detailed catchment study and look in detail what's weathering. But it's quite clear that in these catchments we have very early stage weathering in most of them. And when we look at the actual mineralogy of the suspended sediments and our bed loads, it's mostly just albite that's weathering actually, so plagioclase. We don't see much alteration of anything else until we get down on the floodplain. I'm not sure that answered your question.
But then the rock composition wouldn't really matter that much. So the algae
Yeah, no,
usually
yeah, yeah.
coloration.
Yeah. No, but I guess that's not a bad thing. It seems like a good thing, but we don't have to worry so much about the primary lithology. And it is always a question of we're treating all these sediments, as a bulk sediment sample. When I normalize the data, I use the bulk value to normalize it. But that doesn't mean that that's the same composition that's dissolving. If we would just pick out our albites, they might have a very different composition, and they're the ones that are dissolving. So that's obviously a more accurate way of doing it that you can do if you have time and you want to. And it would obviously show a more precise.
At the same time, if I understand well, the lithium is not equally concentrated in these minerals, so this in any case can have some influence.
Yeah. Definitely. So we actually don't have that much lithium in feldspars. More in maybe potassium feldspars, but they don't weather very easily. They actually weather much harder than an albite, for example.
That you have so much albite in this type of rock.
Yeah, there's quite a lot. We have looked at them more carefully. I can't remember now. Might be around 30% even.
From what you know from the Himalayan, there's a lot of what's called Barovia metamorphosis on fibroid, which have a lot of plagioclase.
Yeah. We kind of lumped that together to say that our web is the same way as albite. So I think I should say plagioclase instead of albite.
I'll try one more.
Yeah.
Maybe that's stupid.
No, it's good.
All right, so the trend is that bulk lithium isotopes in this Paleogene curve increases. Now you're telling us essentially that slow reactions that require a lot of precipitation reaction to remove the light.
You need to have had more.
Right, so if you then look at the million-year time trend, and if you say that this is the process, so you need a system in which residence times are reasonably long for light lithium to be removed.
Yeah.
That means tectonically you need to have the development of a floodplain in order to get a lithium isotope composition. So if I were to ask the tectonicist, then I would, in principle, if I would just say, okay, like take two tectonic regimes like the Andes, for example, and I just, look, the Andes, they go straight down into a subduction zone. nothing happens because the Andes just basically get eroded without much fractionation. Whereas if I have something like the Himalayas, I get the development of the floodplain.
You do have the
And
Amazon.
I do have a very different lithium isotope effect, depending on, so not depending on whether I uplift the Himalayas, but more depending on whether I have a floodplain effect or not.
So importantly, this floodplain contains lots of eroded material from the Himalayas. So you can't just have shield, for example, a flat shield. You still need to have lots of input from material that can weather. So if you look at shield rivers, they actually have very low concentrations and very low isotopic compositions. You don't have much weathering because it's not any material that can weather. So the Ganges floodplain is special because you have so much material that's just dumped there. And that can then spend lots of time there to weather. And I mean, it's from the Andes, you have the Amazon floodplain, where essentially the same thing is happening. So you do have that there.
But the amount of material that is eroding down the Amazon compared to what is going off to the west.
Yeah.
Um,
Yeah. I'm not sure the fluxes, but I don't think you can compare it to the Himalayas anyway. The sedimentary flux. It's
just,
like, not that it's a competition.
thinking
Yeah, but I read that the Ganges provide 30% of the global sediment flux to the ocean. 30%.
yeah.
That's a lot.
But in the sea, it doesn't matter that how is the weathering once it arrives in the sea.
Of the sediments.
Yeah.
That's all.
It's the one who works with
I
that.
think that it's really continuous in the ocean.
Once it leaves the continent, I'm out.
Yeah.
The weather is continuous in the ocean. That's all. Yes. So there's 1 or 2 years.
Do you have a higher weather rates at the Bay of Bengal or the Bengal fan compared to like?
No, this is
Madeleine?
tricky because in a way it's very similar. The retention time is critical. So it's a function of certain barriers. And then in the meantime, the amount of organic matter because that's where you produce your CO2. And then so the simple answer to that is no. No. And then we still don't know why it's that. Yeah, but it seems like we still a lot of factors like retention time, well, there's no uplifting, of course, but the supply, how much supply into the ocean may play a role, but we don't know how. Yeah, so you see the player there, but you don't know whether it plays the same way as you see on land.
No.
So,
Interesting.
and because of the type of element, the type of mineral is dissolving in the ocean must be very different from land.
Yeah.
The time scale is different, and then the marine only gets what's left over.
Yeah.
Right, this is those difficult to chew.
Yes.
So yeah.
It's interesting.
Okay.
I
Well.
don't know.
Okay. So thanks for coming. Well,
Thanks for listening.
yeah. So she was living here. We are going out for dinner, drink. If you have interest, arranging your people's, you're all young. They come to the house. So she'll be in shock. And I will join you guys in it. Yes. So, but I really have wrong. Yes. Okay. Okay. Thanks for coming.
Thank you. Is it still sharing to you?
You can just leave it. Yes, it's still sharing, but you just leave it. Yes. Okay.